All right, so I'm going to be talking now about how I personally got interested in this topic of auto research. And maybe this is a somewhat grandiose title, but I've seen, I called it an AlphaGo moment because of two things. One, superhuman results, but also sort of very shocking and kind of like alien results. In the sense of, in AlphaGo, there was this famous move that the AI made that was just something that was so different from what any Go player would ever do, any human Go player. The experts saw this and thought that's clearly a mistake. That makes no sense. But it turned out actually to be a really good move. It just was like an alien move. And I'm going to be talking about some things, moments like that I've seen in this auto research exploratory process in the context of numerical methods. So a little bit background on myself. I did a PhD at Stanford on focusing on convex optimization with Stephen Boyd. And I also created this open source package, CVXPy, which has become the main way that people use convex optimization in Python. Very, very widely used across many, many industries, particularly finance, energy, logistics. I've also worked in a lot of different fields, particularly energy, where I was at Gridmatic for 4 years, which is an energy startup. And now I'm building GPU native solvers at Optimal Intellect to try and bring all of these numerical methods into the AI era. In terms of a little bit of context, when I'm talking about optimization, this is what I have in mind. So the idea is you're trying to find some solution X, which is like your minimum, your best trade-off portfolio between risk and return, or it's like the minimum fuel use trajectory. It's a very high level kind of way of framing what you're trying to get out of this computation. And I have some objective function, which is scoring X, right? And this is of course how neural nets are trained, right? So this is sort of a universal methodology. But here we also have hard constraints, and this makes it different from like what you would do in PyTorch. It makes it more complicated in many ways to solve these problems. So I have hard constraints where no matter what happens, I'm not willing to accept any X that violates these constraints. So like my trades can only take on so much risk. There's an absolute hard limit. Or my vehicle can only go so fast. Like there's hard physical constraints about what's possible, and I really care deeply about enforcing those constraints. So the constraints are what makes this complicated. So this is what I mean when I'm talking about an optimization problem at a high level. And this approach to computation is taken essentially everywhere decisions are made, sort of high stakes, important automated decisions. It's used absolutely everywhere in finance. Like every major hedge fund, the quantitative hedge fund solves a portfolio optimization to choose what they're trading. It's also used by the power grid. So like just the power going to your house is determined by solving optimization problems, like every 5 minutes. Logistics, supply chain, these are all optimization problems as well. So like Amazon, your packages coming in, right? There's an optimization in that. Really interesting applications, for example, in aerospace. It was someone from Stephen Boyd's group actually who wrote the code that landed the SpaceX rockets. He's still there working on that and other things. So this is also an optimization. It's a very powerful framework for decision making. And as I said, I've been working on solvers more recently for these problems. And this is really difficult. It requires a lot of expertise in math and algorithms, but then also a lot of expertise in high performance code and like CUDA, right? It's quite a lot of skills that you need to bring together to make these solvers. And in some cases, it's even more than that. There's actually, particularly for these mixed integer problems, which are kind of an NP-hard optimization problem, there's actually even like secret knowledge that the solver companies have accumulated over the years. So that even if you just read a bunch of papers and tried to make this yourself, you just couldn't do it. It's not possible. So there's quite a lot that goes into this. And generally the outcome is 3 tiers of performance. There are a lot of open source solvers. You can use those. People are always making new ones. They work pretty well, right? But if you want higher performance, you need to use a commercial solver. something like Gurobi or Mosaic is a nice one too. And these are general purpose because, as I said, it's quite difficult to make these solvers. You need to sort of amortize that work across many use cases. So you build a solver that it works for many situations. But it's not necessarily optimized for any specific situation. And so the third level and highest level of performance is if you make a specialized solver just for your specific application. And this is, for example, what teams will do at hedge funds. Like really large company hedge funds will have an optimization team just focused on improving the decision-making routines that are doing portfolio construction and other things. And they'll obtain performance that's better than what you can get with the general purpose solutions. Now, ideally, you would have, if you had like infinite budget, you would use a specialized solver all the time for every use case, right? But this is, as I said, this is like very complex numerical code, right? This is not really a feasible thing to do until very recently with coding agents. And so what I've been looking at in the last couple months is how do you generate specialized solvers using coding agents, using orchestrations of coding agents. And this is a very new capability. I tried this with Opus 4.5, didn't work, wasn't possible. It was only Opus 4.6 where this actually started working. And then, and also with O3, other things. So this is a very new capability in the models. And the results have been incredible. I'm routinely seeing 1000x speedups over general solvers through this hyper specialization. And the agents have not invented any fundamentally new algorithms, but they have made some really unusual design choices that I'm going to be talking about. So it's like an interesting perspective on the ways in which these agents can be creative. As I said, AlphaGo, there was this famous move where the AI did something that just no human would ever do. It was just so bizarre. And that the Go experts who were watching this were just really puzzled by this decision. And this is what I've started to see with the coding models. Really like surprising decisions. And I've been telling my optimization friends about this, like people from our group. It's really strange stuff. And so I'm going to go through 3 specific things that I saw. The first one had to do with the idea of convergence. How long do I run the algorithm for? The normal way this works is you have kind of a while loop and you have some sort of condition for stopping because you don't know how many steps it's going to take. It's unpredictable. It varies by problem. So you just have to kind of keep running it until you know somehow that it's converged. Okay, so this is how they almost always work. There is one alternative that I've seen before for real-time systems. You might just have a fixed time budget. So then I'll just say, I'll just run like 20 steps no matter what, because there's no benefit to solving it faster, right? I'm solving it like a fixed clock speed. So, at like 100 hertz or something. So I have a fixed time budget to solve. And so I might as well just run a fixed number of iterations. That's the other approach that I've seen before. But the agents did something different that I have never seen before, and I think is novel. They added a problem analysis stage up front, where we'll look at the problem instance, and then it will choose how many iterations to do up front. And then it will just execute them as a single kernel, or like a coup de grace. And the reason it does this is because it doesn't want to do a GPU sync, right? So in order to check the convergence, you have to there's like a conditional logic that has to happen that asks you to do so. It has to go to host. You have to do this GPU sync. And when you're pushing for the absolute limits of performance, you want to avoid this as much as possible. And so what it came up with is this idea of first analyze the problem, then pick how long you're going to run the solver for. And this depends in some extent on like empirical properties of like the data distribution, things like that. And like when I explain this sounds like fairly reasonable, right? But like I really had not seen this before ever. So to me, this was quite shocking when I saw this happen. And I will say, like, it doesn't like say, oh, I'm doing something crazy. It's just looking at the code, I see these things happen that are just, and then this is me abstracting it out, right? So
question.
Yeah.
Wait, so is the mapping from problem properties to iteration count like some deterministic thing that it's writing, or is it like reasoning about it? And then...
That's correct. It's a deterministic function. So ultimately, the solver output is there's no LLMs involved in that. It's just a deterministic solver. I mean, there could be. That would be really interesting. I think that they would be too slow.
But I think he's asking about the problem analysis.
Yeah. No, I agree. I'm saying the problem analysis is part of the solver.
Okay, got it.
Because ultimately, the point of the solver is you give it a problem instance, and then it has to go as fast as possible. But yeah, no, you could do it in other ways too. Like if you had a very slow problem, you could, yeah.
When you say it's deterministic, is it deterministic but like learned over many instances?
So concretely, it'll do things. It usually will look at like the dimensions and the conditioning of the problem. So it will come up with sort of hand-coded rules that
is it like a black box sort of thing?
It's not learned. It's not learned. I mean, you could do that. That would be really interesting. I haven't tried that. This is hard-coded rules that are very interpretable. Yeah.
You said that you kind of picked out this novelty. That did you try sort of feeding it back in and saying, like, is there anything that you've just done that you think is novel, or whether it would have also identified that itself if you had asked it?
Yeah, I did ask it, and it did sort of say, oh yeah, this is novel, which it doesn't always say. It will usually identify something in the literature, because I wasn't sure if people did this or not. So I spent a while like looking. So it did identify it as novel, but I think when it came up with it, it wasn't trying to be novel. It was just reasoning like very, very carefully about its like sort of unique situation. Because the reason no one would do this before is because you really have to care about like microsecond level speedups. Otherwise, this doesn't make that much sense, or like hundreds of microseconds. So yeah.
Do the analyses at all resemble kind of standard analyses on like convergence proofs and things like this? Is it do they end up just being, do they end up being like sort of more detailed, more fine-grained versions of this? You don't bound terms that are typically just bounded away for sake of ease.
Yeah.
Is it a distributional? You mentioned a distributional aspect.
Yeah, so it tends to be pretty simple convergence analysis kind of things. So like the problem where this first came up, there was this one parameter that controlled like the strong convexity of the problem, and it used that. And then I think it looked at the dimension, no, it just looked at that parameter. Then for other cases, it would look at like condition number of different inputs. So it's like stuff that makes a lot of sense. Like it's what stuff you would use in a convergence proof. So like another perspective is that it's derived kind of like a worst case convergence, it's sort of empirically. That's another perspective on what happened here.
Right.
Yeah.
But there's no level of sort of adaptive learning once your optimizer has been constructed. It's really just the
so like I think it's all artifacts of the setup in some way. So the way I set it up, I give it like a benchmark, and it can be randomized, or there's different ways to do the benchmark. But it has like something it's trying to hill climb on. So, but if you had more like a more complex evaluation, it could do something different. Like it's very like I'll get into this even more. It's like so hyper specialized. It really, really depends on exactly what you're asking it to do.
And it has access to the complete data a priori?
Yeah. So I have the setup is fairly, it's pretty straightforward. It's just, at least conceptually, it just sort of has some benchmark, and it can look, I see, can it look at the benchmark problems? No, it's not supposed to.
No, I wasn't looking at it.
Yeah.
Oh, okay. No, actually, that's quite
it's not supposed. It's actually been pretty difficult to get this to work well. The agents will try and cheat any way they can. So I have to fight with them a lot to make them do something that is not cheating. And when I first saw it do this, I was like, geez, it just cheated again. And so it just cheated again. But then I tried it on a bunch of other problems that weren't in the benchmark, and it worked. And I was like, wait, what just happened? This is so strange. It was only after I tested it a lot that I was like, wait, actually, maybe this makes sense as an approach. Yeah.
Is it all going to be optimized here simplex or with found cache? Something else?
It varied a lot. In this particular case, it was the proximal operator of something. It was the total 3D total variation norm. So I was talking I was just asking people what problems they wanted accelerated. So it's minimizing a quadratic plus a sum of L2 norms of the total variation just being a linear operator, just the differences in different directions. And this was for like an MRI kind of setup, or like maybe it was CT. Yeah, it was CT setup. So it's doing a reconstruction from CT, computational tomography, I think. So it's that was the specific situation, but it's done this for other things too. Like I tried it a lot on this QP that had to do with like contact forces. It did something similar. So it's come out, it's mostly, generally the algorithms that it's best at are kind of these, what are called first order methods that are fairly simple. It doesn't do so well if things get more complicated. There are limits to its capabilities, yeah.
In the context of neural network training, it's common to treat the convergence criteria as learning rate scheduling, where you converge a given learning rate, reduce the learning rate, converge given that learning rate, and where the schedule is often meta learned as a research proposal. Is it the case that this model took that kind of idea to this new context, or do you have a sense of the thinking process? Was it transfer, or was it something else?
Yeah, I did dig into this, and I really think why it did this, like the thinking process was because of it was reasoning like very thoroughly about its sort of unique situation, which is running on the GPU, trying to be absolutely as fast as possible on this particular benchmark. And so it identified this idea of, I don't want to do a CUDA sync. And so given that, it's possible, I think what you're saying does make sense. It's probably inspired by that sort of topic. But it didn't, I asked it for like references, like, is there something similar? It didn't really provide anything. So it really seemed to be just reasoning sort of from first principles about its like concrete situation.
I ask this, the auto research perspective for optimization could be automating transfer between optimization subfields that typically don't talk to one another.
Yeah.
Which could be tens of thousands of research projects run one parallel.
Yeah.
With simultaneously review the trends number. In retrospect, obvious improvements that just come out of deep learning researchers and optimization never working on complex optimization.
Yeah. I mean, that's exactly where I want to take this. I'll talk about this in a second. But yeah, go ahead.
Oh, well, I was just going to say that it sounds by the example you used that the total variation distance is, well, it's a norm, right?
Yeah.
So it's got this natural sort of convexity.
Yeah.
Some notion of strong convexity. So is it just, when you were saying this, I was like, okay, maybe it's just doing a normal sort of 1 over mu convex like analysis, and then just saying, well, the natural generalization of this is blur, is the smoothness parameter of the total variation distance. I mean, it's distributional, but fine. And then doing a standard analysis. I mean, I've seen quite a lot of this before that you kind of, it's actually what I do if I can't be bothered to do the analysis myself. It's like, okay, well, run this analysis, but with this norm. Is it that the kind of the flavor of it, or what's... I
mean, it did seem to be referring, like when I asked it why this was a good idea, it did kind of say, oh, well, the convergence rate depends on this parameter. So, but I still so it makes, I think that is maybe the closest analogy is like a worst case, convergence bound, but I really haven't seen it used in this way before, like this, like that, because those tend to be very conservative, right? So you wouldn't, right? So this is different in some ways.
So it's conditional worst case. So worst case conditional upon, for example, the hardware I have to use, or worst case conditional.
Well, I mean, it's somewhat empirical, yeah. The number of steps it chooses.
Feel free to take this offline.
Yeah, I think we're gonna. Yeah, we have a lot planned, so I should probably just go finish my talk, and then we can talk more offline. Okay, thing number two, surprising thing number two, in these solvers you have these things called dual variables, which they have to do with like this sensitivity of the objective to the constraints. They are interesting. Generally, the user is not asking for the dual variables. They usually don't care. So like you'll return X, like the thing you're trying to find by solving the problem. And the duals you usually throw away. But the solvers use the duals like very heavily, and it kind of, it'll try and converge both the prime, it'll try and find the optimal primal and the optimal duals. But the reality is like you're not using the duals after you solve the problem. And so when I set up the task, I only asked it to produce the primal. I didn't ask it for the duals. And so it actually exploited this in a way that I hadn't really seen before, where it just in every possible way made the duals second class objects. Like it used lower precision floating point for the duals. The solver didn't actually even really converge the duals like to any sort of reasonable accuracy. And this was the total variation thing. Yeah, it sort of played in with this idea of the problem analysis, like because normally for the convergence checking, you would need the duals to be converged. So the fact that it was doing that differently kind of enabled this. So this is something that I've thought about this for so many years. It's like we just produce these duals and then throw them away. But I hadn't really seen that exploited like so like systematically before. So that was another new thing. Happy to talk more about this offline. Right, so as I said, treated the duals differently. Okay, this is the craziest thing that it did. So I asked it to make a solver for like a very specific problem, like non-negative least squares with a dense block, like really specific stuff, total variation. Like I assumed that it would make one solver because this is like really specific. In many cases, it actually made like 10 solvers. And it would dispatch based on like the dimensionality or like the like condition number of the matrix or like various other things like related to this problem analysis. So, I mean, this was another thing where it's like, wow, that is so strange. And like when you see what it did, it's like, okay, that makes sense. Like if it's very small, maybe it's like more analytical. It would sort of, there's these things called active set methods that are more discrete, and it would kind of transition from that to more continuous methods. So this was like, and really surprising to me. Like I thought I was being specialized by asking for this one solver, but it like went way beyond that, right? It made like 10 solvers, and maybe it could have done more if I had had a larger benchmark. And so this kind of gave me an idea related to sort of the question earlier about sharing knowledge across many problems. Okay, so right now you have kind of like a rough idea of what algorithm is good in a different situation. Like if you asked me or my advisor or someone what you should use, we may have some rough idea of what is best, but you could really map this out using these tools and then across many problems as well, right? You can do like broad knowledge sharing and build up some knowledge base. And like, who knows what you would find? I think it's really totally up for discovery. Like there could be totally new algorithms because there's just some region that, people haven't really focused on. You could have hybrids between known algorithms. I think you definitely would. I've seen this to some extent. There's some deeper like commonality across all these algorithms. And there's like, you could even learn some representation of all the algorithms where you can just say, oh, I'm here, then I should use this algorithm. And have knowledge transfer across algorithms. So this is like an example of where the scale and the systemization could come into play. Because I've just been doing this kind of one problem at a time. But given enough compute, you could do this like, this could be a massive effort, like millions and millions of problems.
You use this to propose new algorithms. Basically, you could imagine intuiting the properties of the algorithm should have from the parameters that determine the point the algorithm weight space that would be optimal for that problem.
Yeah, exactly. I think that would be the most like, if that would be the greatest efficiency and like maybe one of the more interesting things you could get out of this is if, because it's very expensive and it takes like a long time to produce one of these solvers. So if you can have a learned representation that then you give it the problem structure and then it produces the solver, that would be, I think, a much better way of doing the specialization. So in conclusion, this sort of specialized solver generation, I think, is a really interesting example of automated discovery at scale and the sort of possible like lessons you could learn from it. And I do think there's this way that I was interacting with AI is perhaps like one model for how a human is in the loop for this. Because all these like strange things that it did that I shared, it wasn't really like saying, oh, I'm going to do something crazy now. It just was like looking at the code, looking at what it produced, and sort of reflecting on my experience making these solvers that I'm able to like make these sort of more abstract, like conceptual statements about what it did. Because that wasn't really how it was thinking about it. It was thinking about it in a much more narrow context. And I called it, all of this whole concept, I've been talking about optimization, but all of applied math, I think, should be extremely approachable through this sort of methodology. So obviously linear algebra, differential equations, like all sorts of physical simulation should all be approachable through a pretty similar methodology. And so I really feel, having seen this now over the last couple of months, that applied math is going to be totally transformed in terms of our understanding of what's possible and sort of the landscape of applied math. All right, well, thanks so much. I really appreciate all the questions. Yeah, but we'll talk more offline.